Number 32. The pressure drop along a length of artery is 100 Pascal. The radius is 10 millimeter and the flow is laminar. This average speed of the blood is 15 millimeters per second. Letter A. What is the net force on the blood in this section of artery? So here's our artery. We have two locations, P2 and P1, and it's telling us that the pressure drop, meaning the change in pressure. That's basically what pressure drop means. Okay, it means delta P. So it tells us that the change in pressure, or the pressure drop, is 100 Pascal from one location to another. So in other words, P2 minus P1 is equal to 100. That's also the same thing as saying delta P. Now, it also tells us that the velocity of flow and the radius. Now, the idea here for letter A is if we think back to just the simple pressure equation, right, back from the last chapter, the pressure is equal to force divided by area. We can slightly reorganize this so that we can get now our delta P in there. So notice that in the two particular locations, I'm calling this location 1 essentially, and this location, this location 2 and this location 1. So notice how the area hasn't, the cross-sectional area that is, hasn't changed, right? The radius is still going to be 10 millimeters, which I, by the way, converted to meters, right? I also did the same thing for the velocity, converted that into meters, just so you know. And we realize that if the area here isn't changing, then how is the pressure changing? Well, it's basically a result of the force, okay, according to the formula. So in other words, we can say that the change in pressure is equal to the net force applied divided by the area. Reorganizing this, we can say that the net force would be equal to the change in pressure multiplied by the area. Cross-sectional area, that is. So look, we know the change in pressure. That's in Pascal, so that's great. And we can find the area, right? Because the cross-sectional area of a cylinder is a circle. So we know that now the net force will be equal to this change in pressure multiplied by pi r squared. And we know all the values now, right? So let's just plug it in. So this is 100 multiplied by pi times then r squared. Remember, it has to be in meters. I already converted that. So all we need to do is just plug it on in, right? So here we go. So it's going to be 100 multiplied now by pi and then multiplied by 0.01 squared. So we get a value here that the net force is about 0.0314, and well, that should have been evident. I did, and this is now in newtons. All right, so there we go. So there's the net force that takes care of letter A, and now for letter B, what is it asking? It's saying what is the power expended maintaining the flow? So we have to remember the formula for power, right? Average power is going to be equal to the force multiplied by the average velocity. So they told us the average velocity is 15 millimeters per second, but remember we need that in meters per second, so I already did that conversion. So all we now need to do is basically plug in the result of this, right, for the force, 0.0314, and then multiply it now by that velocity in meters per second, 0.015. And here the pressure will be in terms of watts, 0.0314 times 0.0, well, actually let me use the exact value. So that exact answer from before times 0.015, and we get 4.71. 4.71 times 10 to the minus fourth, and like I said, that is in terms of watts. All right, guys, so there you go. Thanks for tuning in. Appreciate it very much. Please remember to subscribe. See you next time.